Let's say we want to write a function which, when given an argument, just returns the argument back. Ignoring the type signature, how exactly would we write that function? Well, here is a function which we have called inout, and it does exactly that. Whatever you call the function with, the value is returned. And as you can see here, when we call the function with any type, it will return the value that was passed in. Here we are calling it with a string, here we are calling it with an integer, and here a double. And here is a bool. And everything works as expected and the value is returned. The question is, what exactly is the type of this function? Well, let's ask GHCI what it thinks the type is. When we ask for the type of this function, it says it is of type A to A. Now what exactly does this type signature mean? Notice how it is a lowercase being used for the type name. Every example we have seen so far has had the type name start with an uppercase letter. Concrete types always start with an uppercase letter. For example, string, int, and all of the custom types we have defined so far. However, a type name beginning with a lowercase letter in a type signature actually represents a type variable. This means it could be any type. The type is said to be a type variable because the type varies depending on the type of the argument of the function when it is called, like we can see here, where the types of the arguments are string, integer, double, and bool. And so the type signature becomes string to string on this function call, because it takes a string and returns a string, and then int to int on this function call, and so on. Type variables can be given whatever name you would want. For example, we could have given the function this type signature, or we could have given it this type signature. Neither of these type signatures actually improve the situation compared to the simple A to A type signature. So since longer type variable names don't actually improve readability of the code, we usually just give a type variable a single character name like A, B, C, or D. One thing that you should definitely note about the A to A type signature is that the same type variable is used as the parameter type and the return type. This puts the restriction on the function that whatever the parameter's type is, it will be the same as the return type. A function which contains type variables in its type signature is known as a polymorphic function. Polymorphic literally means of many forms, which makes sense here since we are talking about functions which will work with any type. And so this can be read of as, for any type A, inout takes in an A and returns an A. There is already an inbuilt function which is defined in the same way we have defined inout. That function is called id. You can see the type signature for id matches the one we see for inout. Let's explore a few more built-in polymorphic functions. There is the fst function, which is pronounced first. It takes a tuple of type A and B and returns A. Take a second to think about what you think this function actually does. If you said it returns the first value of the tuple, then you are right. Let's take a look at this type signature. There are two type variables, A and B. Type A could be anything and type B could be anything. The type A is the type of the first parameter in the tuple and the type of the returned value. And so, this acts as a sort of constraint for the values that can be returned. The first value in the tuple and the return value of the function must have the same type. The type B can be anything. There are no constraints in the signature, so it could even actually be the same as type A. We can call the function like so. Here, in the first invocation, the types of A and B are the same. They are both strings. In the second invocation, they are different. A is an integer and B is a string. Another inbuilt polymorphic function is snd, pronounced second, which has the following type signature. You can probably guess from the type signature that this just returns the second item in the tuple. And here are some example usages of the second function. Two more examples of polymorphic functions in the Haskell prelude include head and tail. These are polymorphic functions which act on lists. Both functions expect you to pass in a non-empty list and will throw an exception if you pass in an empty list. Head takes a list of A and returns an A. It extracts the first element of the list and returns it, as you can see here. Tail takes a list of A and returns a list of A. Tail returns all of the list except the head. In other words, it returns all of the list except the first element. Since these functions throw an exception if you pass in an empty list, they are not really used in production code, but they are good enough for learning, so we will be using them quite a bit. When you have a type variable in a type signature, it is known as a form of parametric polymorphism. This is because the type variable is kind of like a parameter in the type signature. Let's understand this further by focusing on the ID function. We know that the type of the ID function is A to A, meaning it can take any type and will return a value of the same type. Now when we call the function with a string, it returns the string like we expect. In the case of this function call, since we know the parameter is of type string, we can conceptualize the type signature for this particular function call actually being string to string. At the time of the execution of the function, it is as if the type variable A in the type signature is given the value of string. It is the same when the function is given an int. You can think of A as being an int in that case, and so on for any other type. Hopefully now you understand what we mean by parametric polymorphism. Parametric because there is a type parameter, and polymorphism because the function has many forms, one for every possible type. You will see parametric polymorphism everywhere in Haskell, and so you will get used to it quite quickly. In a previous module, when we were discussing algebraic data types, we saw how we could define our own custom types, and we made a distinction between the type constructor and the data constructor. If you remember, I used the example of a dateTC type, and I explicitly named the type constructor dateTC and the data constructor dateDC to make the distinction between the two clearer. We saw that we could view the data constructor like a function, which takes in parameters, in this case 3 ints, and returns a value of the type. Just like the data constructor, the type constructor too can take in parameters, but so far every type constructor we have seen has not taken any parameters. This has been on purpose to keep things simple. I mentioned in the previous module that we would eventually look at type constructors which take parameters too. That time has now come, and we are going to cover that topic over the next few minutes. One of the simplest examples of a parameterized type is the maybe type, which is defined in the standard prelude. It is defined as maybe A equals just A or nothing. As you can see, the type constructor has a type parameter, which we have named A. The type constructor parameter, which is declared on the left of the equal sign, is available to use as a type parameter to any of the data constructors defined to the right of the equal sign, which is what the just data constructor does. It takes in a type of A. The nothing constructor is a nullary constructor. It does not take in any parameters. Let's take a minute to see how we can create values of the type maybe. In this case, we are creating two values, m0 and m1. Both of these values are declared with the type of maybe int. Remember, in the type signature, we refer to the type constructor, and when creating values, we refer to a data constructor. In this case, the type constructor does not share its name with any of the data constructors, and so it is easy to see what is being invoked, but in other cases, they may share the same name, so you should be aware of the distinction. Type signatures refer to type constructors, and to create a value refer to data constructors. The value of m0 is set to nothing, and m1 to just 43. Nothing does not take a parameter, and so we can create its value by simply invoking the constructor. However, the just constructor has a type variable as a parameter. The type will always be the same as the type passed into the type constructor, which in this case is an int. So when we call the just constructor, we must pass it an int. In the next examples, we are creating three values, m2, m3 and m4, all of which have the type maybe string. m2 and m3 are invoking the just constructor with a string to match the type in the type signature, and m4, just like m0, creates a value of nothing. Now if we inspect the types of the data constructors in GHCI, we can see that the type signature for the just constructor takes an A and returns a maybe A. This is just as we would expect, since the just constructor has a single type parameter of type A. The type signature of the nothing constructor takes a maybe A directly. Now this could potentially be confusing. The nothing constructor itself does not take a parameter in its definition, but then how come when we ask for the type it does? Since the nothing constructor does not use the type parameter A, it effectively does not matter what the type A actually is. Regardless of the type of A, the nothing constructor can be invoked to create a value of type maybe A. The nothing constructor returns a polymorphic value, and so without any explicit type declaration, Haskell will infer the most generic type, which is maybe A. If we provide a more specific type declaration, then the type of the nothing value will be more specific. For example, M0's type is maybe int, not maybe a, and M4's type is maybe string. What exactly is the point of the maybe type? Well, the point is to have a type which indicates the absence of a value as well as its presence. Let's say you want to write a function which returns the first item in a list. Well, the list could be empty, so we could write the function so it returns a maybe of a. Then when the list is empty, we return a nothing, and when it is not empty, we return a just with the value of type a. This is a lot safer than what is in the prelude by default, which is what we have seen before, where an empty list would cause the function to throw an exception. Let's take a look at another parameterized type, the either type. The either type is also defined in the prelude. In this case, it takes two parameters, a and b, and there are two data constructors, the left, which takes a value of type a, and the right, which takes a value of type b. The point of either is to have a type which can represent a value with two possibilities, either left or right. In most cases, it is used to represent either a correct value or an error. The right constructor is used for the correct value. This is because right has the double meaning of the direction right and the correctness right. The left constructor is used to hold an error value. Let's look at a function which returns an either. Here, we are defining a function called intDiv, which takes two ints and returns an either of the string int. The type parameters to either have been given here as string and int, which means the value of the type parameter to the left constructor must be string, and the value of the type parameter to the right constructor must be an int. The point of the function is to perform integer division. That is, take two ints, divide the first by the second, and return the result truncated to the closest downward int. We isolate the case where we are trying to divide by 0, by pattern matching on 0, and return a left result, because it is an error. In this case, we just return a string indicating the reason for the error. And then for the general case, we return a right result, containing the value after performing the actual integer division, using the inbuilt div function. The types of the constructors are exactly as you would expect. Both left and right take a single value and return an either. One of the things you should know is that the a and b type parameters can actually be the same. So you can have an either string and that would be perfectly fine. But when they are different types, as is the case for the intDiv function, then the left constructor is constrained to take a value of type a, and the right constructor is constrained to take a value of type b. The left constructor completely ignores the b type parameter, and the right constructor completely ignores the a type parameter. This is similar to what we saw before with the nothing constructor. When it comes to types, we have already seen some polymorphic ones without realizing, tuples and lists. We haven't realized it because they come with their own special syntax in Haskell. For lists, the square brackets act like a constructor, and so we can ask GHCI what its type is. And we get told that the empty list is of type list of A. The empty list is kind of like the nothing constructor for a maybe. Any type parameter value is valid, since an empty list is a valid value for any type of list. And so just like for nothing, Haskell will show the most generic type for the empty list, which is the polymorphic value of list of A. For tuples, the comma acts as a constructor, and so we can ask GHCI what its type is. So a single comma takes a value of type A, and a value of type B, and returns a two-tuple of type A and B. And when we have two commas, it takes a value of type A, a value of type B, and a value of type C, and returns a three-tuple of A, B, and C, and this goes on for the rest of the tuple sizes. That's pretty much it for now for our discussion on parametric polymorphism. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the LigoLearn channel. See you next time.